Okay, calculus, so we are going to start moving on into chapter 3 now, which is the largest, I wouldn't necessarily say the most difficult, but conceptually probably the most important chapter that we're going to be covering the entire year here. So chapter 3 is a big one, guys, and this section right here is incredibly important, really from a theoretical standpoint of explaining everything that we're going to be doing here within the rest of this chapter and really the rest of the entire first semester. So what we start doing now is getting into, and you'll notice for the first time all year, the D word, everybody. Chapter 3 is all about the derivative, which is something you guys got a little sneak peek of last year in pre-calc, but we really haven't used the word at all in here to this point. So we start getting into, in this chapter and in this particular section now, what a derivative is and what it's useful for and how to go about finding it. So we're going to start off now with this section here on definition of the derivative. And we're just going to begin here by recalling a definition of an average rate of change that we've gotten to before. And we're going to start to see the connection here pretty soon between the concept of a rate of change and that of a derivative. So the formula for average rate of change, which you guys really knew coming in here this year, but we went and discussed in a little bit greater detail early on in chapter 2, was simply this: that the formula for average rate of change is f of b minus f of a all over the quantity b minus a, otherwise simply known as delta y over delta x. And I just want to recall one more time then that what we were doing right there when finding an average rate of change was really the exact same thing as finding the slope of a secant line. All right, these two things went hand in hand here, everybody, so that, not quite sure why that is there, anytime we had a graph, and it didn't really matter at all what kind of curve we were dealing with, we could come up with an average rate of change by finding two data points on that curve. So maybe just randomly we would choose one right here and let that x value be a, and then another one somewhere else at an x value of b. And the line that was formed, I guess I usually did this in green, the line that was formed by those two data points on that curve was a secant line. So the definition we wrote down for a secant back in chapter 2 was a line defined by 2 points on a curve. And an average rate of change is defined by using two data points. And they're right here if you're looking for them. A is your starting x value, and f of a is the starting y value going along with that. B would be the ending x value, and f of b would be the ending y value. So this formula right here should definitely look familiar to you guys. The formula, delta y over delta x, is simply the formula for the slope of a linear function that you guys have been using for multiple years. So that was just meant to kind of refresh our memory just a little bit here before we dive into the big concept, which begins on the next slide. But let me just take one last opportunity to point out that these two concepts here, an average rate of change and the slope of a secant, both require 2 points in order to be calculated right here. And what we are really interested here, and we flirted with this idea just a little bit at the beginning of chapter 2, as we were starting to begin the process of limits, is that it really wasn't all that difficult, it wasn't all that complicated to find one of these two things: an average rate of change or the slope of a secant. But what we really were interested in as we moved on was finding not an average rate of change, but an instantaneous rate of change. And we said that in order for that to happen, this quantity right here, b minus a, would have to get smaller. Basically, that either a would have to move over here to the right to get closer to b, or maybe b would have to move closer to the left to get closer to a, or maybe they both move to hit some spot in the middle. And what we wrote then, everybody, in chapter 2 was that an average rate of change would become more like an instantaneous rate of change as your denominator, in this case b minus a, approached 0. And that's really the big idea at work here when we start talking about this. So this sentence here is pretty important, everybody, so you want to make sure that we get this one written down. If your average rate of change is equal to the slope of a secant line, then your instantaneous rate of change, or IROC, we call that a lot, is equal to the slope of your tangent. So that is a pretty darn important concept that we want to make sure that we get down. An instantaneous rate of change is the same thing as the slope of your tangent line. And this diagram, which doesn't look super complicated right now, is the tool that we're going to use, the vehicle, everybody, to try to come up with this formula now for the definition of the derivative, which guides everything we're going to do here later on in this chapter. So we're going to begin talking about slope of a secant, and then we're going to let that formula evolve a couple of times in a way that I hope makes sense, and we'll eventually use that to figure out the formula for slope of a tangent, which of course it says in the red box up on the top is the same thing as your instantaneous rate of change. So let's start talking about this, guys. All right, so what I've drawn here in blue is an incredibly generic curve. It actually would still be accurate and applicable if this was a linear function, but it just wouldn't make as much sense. So I think it's probably better if we draw it as a simple curve, and in no way, shape, or form am I trying to dictate what kind of curve this has to be. I've just drawn it as a non-linear function. And what's going on? As I move things here, I don't really love where I put that. That dot should probably have been a little bit more like that. And okay, there we go. So what's going on here, guys? We have a nonlinear function, and we have delineated two data points that are on this curve here. The first one, let me start with this one right over here, has the coordinates of x for its x coordinate and then f of x for its y coordinate right there. And remember, guys, that f of x is not random. If y is given to us as the function f evaluated at x, then this x value here plugged into the function would get us f of x. The second data point, this one located right up here, is named in a way that we have to understand if we're going to grasp where this eventual formula comes from and what it means. Instead of introducing a new variable right over here, like y or n or anything like that, for a reason that I think will become obvious later, we call this second x value x plus h. And I want you to realize what's going on right there. X was already used for the starting value right over here. And this one is now further to the right than the starting point. How much further to the right is it? That amount is what h represents. So this is a variable we're going to be using a lot in this chapter here. H represents the horizontal distance between your 2 points of sequency. Back to this previous formula, we were really using the variables a and b to represent the starting and the ending points. In this case right over here, that a value has now been denoted as x, and that b value has now been denoted as x plus h. And the distance between them is the difference between them. X plus h minus x, and that just gets you h. So this is where we are at right now. And one of the things you're going to hear me say a lot during the course of the year, everybody, is that great progress that has been made within math and science very, very often comes from an idea that builds upon something that is existing, something that is known, something that is already accepted and understood, and then somebody just started playing with the idea a little bit and said, well, maybe I'll try this and maybe I'll try that. And before long, you know, a couple centuries, okay, in human history, all of a sudden then boom, we come up with something amazing. So let's talk about what's going on right here. If we want to define the slope of the secant line, there is only one defined by these 2 points, well, here's what we would do. Probably not a bad idea to draw that secant line right about there. It's not a great line, but that's okay. All right, guys, and there is our secant line, and the way to come up with the formula for slope of a secant is change in y over change in x. So, just like we did on the last slide with f of b minus f of a over b minus a, we're going to do that same concept here, but the names have changed a little bit. If we take a look at the 2 points here, the ending y value, which is the y value at this point right over here, is f of the quantity x plus h. There's your ending y value, minus your starting y value, the y value at this point, which is f of x. So there's your change in y up on top. And then down on the bottom, everybody, it would be the change in the x coordinates. The ending x coordinate, which is x plus h, minus the beginning x coordinate, which is just plain old x. All right, so that's our formula here for slope of a secant. And we certainly didn't reinvent the wheel there, anybody. That's some pretty basic stuff right there that we've been talking about for a while. But now, where are we going to go with that? Well, the one little thing we can do to get really from this line right here to this line right down here, we would always ask ourselves, can the previous expression be simplified at all? And the answer here is very, very little, but it can be. I want to remind everybody that this first term in the numerator right here cannot be expressed any differently than it is. It absolutely is not f of x plus f of h. That would be using the distributive property, which is what we would do if f was a number. But f is not a number, it's not a value right here, it's the name of a function. So that is absolutely not something that we're going to be able to do. So the answer is the numerator can't be simplified at all. We leave it as f of x plus h minus f of x, but as you probably saw down in the denominator, x plus h minus x, those x's are going to cancel out and just get you h right over here. So this is as good as we can make the formula here, guys, for the slope of a secant. But what's important to talk about is something that we discussed in chapter 2 and just a little bit on the last slide. Our overall goal here, everybody, is to get this average rate of change and make it look more like an instantaneous rate of change. Or, to put it another way, to take this secant line and make it look more and more like a tangent line. So to do that, what we're going to do is take this value right over here, you guys, of x plus h, and start sliding it over here to the left. Now, if we do that, let's think about it. This big red dot that's located right there, I'm not sure if I'm going to have any luck moving that thing. Yeah, okay, let's do that. If I moved it right over here, if I slid that a little bit farther to the left, now I'm going to call that secant 1, my second secant line might look something like this. So that would be secant number 2. Okay, and if I move that red dot, if I move that red dot a little bit further to the left, it might come down here, and now the next secant, there you go, might look something like that. That would be secant number 3. And if I moved it even a little bit further, maybe to right about here, this next secant might look something like that, and there would be secant number 4. And we could keep doing this kind of over and over and over again, guys, but I want you to realize what's happening. In each one of these 4 iterations, as we move this red dot further and further and further to the left, the way we're doing that is that this value of h right here is shrinking. H represented the horizontal distance between this x value and this x value right over here. And if we want this secant to become more like a tangent, or if we want our average rate of change to become more like an instantaneous rate of change, we've got to let this quantity right here, h, which you will notice represented the denominator of this version of the formula for slope of a secant, we need our denominator to get close to 0. Now, this was the big concept that we talked about back in chapter 2. Can we ever let these 2 points of sequency become the same point? Because that's how an average rate of change would actually become an instantaneous rate of change. So can h be 0? And the answer to that, I hope you guys know already where I'm going with this, the answer to that is no. If we were to let h equal 0, then what happens is the numerator actually becomes f of x minus f of x, which is just 0. The denominator is clearly 0, and we end up with 0 over 0, which is still undefined. But what I'm thinking you guys know by now is this. If we want h to shrink down, we can't let h equal 0, but we can let h approach 0. And now that we've got something new in our mathematical toolbox that we didn't have before, and that of course would be the concept of a limit, Now all of a sudden this is going to make a little bit more sense. If we want this secant line to become a tangent line, we need to take this value of h and shrink it down as far as it can go. We need to get it close to 0, and if we could let h approach 0, then this value of x plus h would approach this value over here, and those red dots that kept sliding farther and farther and farther to the left is eventually going to give us a second red dot directly on top of the first red dot. And that new quote-unquote secant line is going to look something like this. And it's really defined by just one point on the curve itself. And of course the definition, I think you guys know, we'll be a little more thorough about this in the future, but a line defined by only one point on the curve having the same slope as the curve itself, well, that's not a secant at all, anybody. That there in red is our tangent line. All right, so back to it. Here's the big takeaway from this slide, and really the big concept on the day, everybody. We can take our formula right up here that you see for slope of a secant, and we can turn it into slope of a tangent by taking the exact same formula, guys, although you'll notice I'm leaving some space here. There's a reason for that. F of x plus h minus f of x all over h. That's the formula for slope of a secant, but we can take this secant slope formula and make it become a tangent if we simply let our denominator, h, approach 0. I can't let h ever equal 0, but I can let h approach 0. And if we can figure that out, then boom, we've just come up with the formula, everybody, for the slope of a tangent. What else have we found? The slope of the tangent is the same thing as your instantaneous rate of change. So I'm going to write this right underneath right here. Instantaneous rate of change, that's really the same thing. And here's really the big important thing, guys. We have also found and defined our derivative. So this formula that we have right here is really the formula for the definition of the derivative. And I'm trying to see where we're going to do that well. Let's go ahead and put that back over here, guys, so we don't lose sight of that. That's the same formula for instantaneous rate of change, but let's go ahead and put this one here, guys, so we have it clearly spelled out. The definition of the derivative is the following. And the notation we would be using here, given the way I've got this set up, and I think you guys saw this last year, would be f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. So that is something pretty darn important that we want to make sure that we've got labeled very, very clearly in our notes. That's the formula here for definition of the derivative. And we'll spend more time over the next few days or weeks actually discussing what it is that we've actually found here on the left. Okay, so that being said, this is some stuff that wouldn't have been a bad idea to discuss before we got into that example, but let's run through it right here. The definition of a secant, I've said this before, but I'm not sure we've actually written it out. A line defined by 2 points on a curve. Now, when you guys first learned what a line was 3 years ago in geometry, you simply said it's the set of all collinear points with two given points there. You started with point A and point B and hit everything between them, and there was your line. Now with a secant, we simply define those 2 points as being located on a curve. But the important thing there, a secant is defined by 2 points on a curve. You want to make sure that you understand secant requires 2 points. A tangent, however, is a little bit different, guys. A tangent is a line defined by, and this one is going to be only 1 point on a curve. But unlike the definition that we just got done writing for a secant, there's more that needs to be said about a tangent, and here's why. If we had a curve, let me just draw something quickly. I don't think you guys need to put this in your notes here, but if we had a curve and I chose 2 points and said this was point A and this one over here was point B, and I asked you to draw the secant line between points A and B, I said the, not a secant line, because there's only one. One of the basic postulates of geometry is that there is only one line that passes through two distinct points. So simply saying that a secant line is defined by 2 points on a curve is good enough for us to define this line uniquely. There's no other line that passes through points A and B. However, if we were now going to talk about a tangent line, and I asked you guys to draw me the tangent line that passed through point C, well, the definition we just wrote down is a line defined by 1 point on a curve. Okay, so we're going to focus on point C, but the problem is this. There are an infinite number of lines that pass through point C. Let me say that again. There was only one secant line that passed through A and B, because 2 points define a unique line. But with the tangent line we're about to draw, all we know is that it passes through C, and shoot, you guys, there's an infinite number of lines here that pass through point C. We could sit here all day long and continue to draw one line after another that passes through point C. So how in the world are we supposed to know which of those 8 lines or whatever that I just drew, and of course there are infinitely many, how are we supposed to know which one of those is the tangent line? And the answer is we don't yet, because Mr. Fontana stopped writing his definition too early. So let's go back to it, and I've got to finish this now. The definition of a tangent is a line defined by 1 point on a curve, and now here we go, guys, having the same slope as the curve itself, at the point of tangency. And that's a phrase we're going to be using a lot here throughout the rest of this year. Really, everybody. Tangency. Okay, and there we go. A line defined by 1 point on a curve having the same slope as the curve itself at the point of tangency. So now if I went back to this horrible diagram right here, and if I were to just grab as much of this as I could, oh, that's not going to work well. All right, let me just see if I can do this the hard way, guys. Just start, oh, actually that worked really well. Okay, so now let's try this again. What we need to do is draw the one and only line that passes through point C, and boy, this is a weird way of looking at things. We need to draw the line passing through C that has the same slope as the curve itself. Well, let me draw you one that's not a tangent, and that would be this one right over here, just as an example. Now, what I've drawn right here is not a tangent, and here's why. Because that line that we just drew doesn't have the same slope, or it's not parallel to the curve itself at that point of tangency. If you were to zoom in on this real tight, obviously it looks like the curve in black is going from high to low as we move from left to right. It's a decreasing function. But my blue line that I drew seems to be increasing, rising from left to right. So it kind of looks to me like at this spot, the black curve would have a negative slope because it's decreasing, whereas the blue curve would have a positive slope because it's rising. So let's try that again then. I'm going to try, and I used the P word just a second ago, when we talk about two lines having the same slope, those lines are parallel. Well, when we talk about a line having the same slope as a curve, it's really kind of the same concept. We want to draw, as weird as this sounds, a line that is parallel to the curve within this very small little window right over there. All right, so what we're going to do is kind of mentally zoom way in on that and say, all right, my best guess is that the curve itself is moving, I don't know, maybe in that direction right over there, and so my tangent line passing through point C might look something like this. Okay, so to be clear, this is the difference, everybody, between a secant line, which is defined very simply and very easily by 2 points on the curve, and then your tangent line right up here, which is harder to define and harder to draw. It's defined by only 1 point on the curve having the same slope as the curve itself. Now, I didn't mean for this to happen, but it did. I want to go ahead then and point out one of the shortcomings that a lot of you guys have with a definition that's already in your head about a tangent. And I'm going to tell you where you got this idea too. When you guys first learned the word tangent, it was in geometry 3 years ago, and it was when you were studying circles. And a tangent to a circle is a line, oh, that wasn't very good. Let's try that again. A tangent to a circle, that was still bad, is a line that just kind of grazed off it itself. Well, I'm really struggling here, guys. You go away, you go away, you go away. Wow. All right, let's try this one more time. Yeah, that's better. A tangent is a line that just kind of grazed off a circle one time. And in geometry, this is very likely the definition that your geometry teacher gave you, a line that only intersects a circle at one point, as opposed to a secant line, which you also learned in geometry, which crossed your circle twice. Now, those were the definitions for a tangent or a secant to a circle. But unfortunately, a lot of you guys applied that same definition to the diagram on top when we were talking about a curve. And a lot of people are going to tell me at the beginning of the year in calculus that a tangent is a line that only crosses a curve once. And that is incorrect. And you can see why right over here there's a second point of intersection between that blue tangent and the original black curve, and I'll call that at point D. Now, I just want to be clear, D is what we would call an incidental point of contact right there between the tangent and the curve itself. We just need to understand that the blue line that's drawn there is tangent to this curve at point C, not at point D. Okay, so in the way that we've drawn it, that blue line is a tangent at point C. It's also a secant using points C and D. So it really is just a question of how you choose to define it. But there will be some curves out there, we'll see one later in this section, where there is no point D. That never quite happens. So that's where this definition for tangent comes from, guys, and it's pretty important, okay? All right. And here we go. I went ahead and typed this one out for you right here because it's a long time to write. But the derivative, everybody, is one of those things that even after students spend the entire year dealing with it and they know how to find it and how to use it, if you were to ask them to verbally define that, some people still have a hard time coming up with that. So I want you guys to make sure that you have this in your notes and it's something that you can come back to and reference as frequently as needed. And I think it's incredibly important, you guys, just the way it begins. A derivative is an expression. I'm going to stop right there. A derivative is an expression. All right? And what I mean by that, an algebraic expression usually, not always, but usually contains some combination of variables and constants, and then other mathematical operations like addition, subtraction, multiplication, and division. But the derivative is an expression, so it might be 3x plus 5. The derivative might be 2x squared minus 8x plus 3. The derivative might be 7 over x. All right, but it's going to be an algebraic expression in most cases. Let me keep going now. So a derivative is an expression which can be used to evaluate a function's instantaneous rate of change at a particular value of its domain. So what I think is really important right there, guys, is that we're not saying that the derivative is the instantaneous rate of change. We're saying that the derivative can be used to find the instantaneous rate of change. And that's why, let me skip over this spot for definition down to this magical diagram that I drew down here at the bottom. You're welcome, everybody. That's why those arrows right there are one-sided. The derivative can be used to find instantaneous rate of change. It can be used to find slope of the tangent, and these two concepts here are really the ones that are equal to each other. But I am not going to put another equal sign right here and say that this necessarily leads to that. That would be slightly misleading if we were to put it that way. Okay, so I realize now, guys, that this right here, sorry about that, definition of the derivative, that's exactly what I had you write down at the bottom of the page right here. Certainly isn't going to kill us to do that again. If it does, I'm sorry. But anyway, here goes. So again, the definition of the derivative, f prime of x, that's the expression that we are finding, is the limit as h approaches 0, one more time now with feeling, of f of x plus h minus f of x all over h. So we already put this in our notes, we already boxed it up, but I think the more we write that, the faster we're going to get that memorized here. All right, guys, that's that's a lot of definitions going on right there as to what a derivative actually is. Okay, let me skip past this because we talked about that already. And before we actually start finding some derivatives, I've already gotten into this a little, and I'm sorry about that. Let's start talking about notations for the derivative. And if you're not familiar with the word notation, it simply means a way of writing things. A notation is a way of writing usually particular numbers that can be a little bit messy, but here we go. Now, two names that you're going to hear mentioned a lot in here this year are those of Isaac Newton, who everybody who's taken physics already knows who that is, and then somebody you've probably not heard of before named Gottfried Leibniz. And these are the two mathematicians who are most notably credited with the discovery of calculus. Now that right there is funny already. Normally you'd say or you'd think that calculus was something that was invented, but within the scientific and mathematical community they tend to prefer the word discovery, and if you think about it you understand why. An invention is something that wasn't there before that you then came up with. But a discovery is something that was always there and someone then just happened to stumble upon it. And mathematicians like to think that all of the cool stuff that's going on in calculus was somehow preordained by the laws of not man, not God, but science and nature and the world as it is, and that this wasn't up to a human being's choosing or invention, that they just found it. It was there. Now anyway, Isaac Newton is the one that we credit the most with using the f of x notation that you all know and love. Just kidding. Most people prefer Leibniz's notation, which is y right down here, but we're going to be using these two interchangeably throughout the course of the year. All right, guys, so if we're going to use Newton's notation, and if we're going to call our original function x, then the derivative of that function, you already saw me use it a moment ago, looks like this. And if you're typing, you'd use the apostrophe key on your keyboard right there, f apostrophe x, but of course we read that as f prime of x is the way we would read that. When we get in later on in this chapter to second and third and fourth derivatives, we would do just a little double mark right there and call that f double prime of x. We would do the same thing with f triple prime for the third derivative, but eventually, if you were to ever get to a fourth or a fifth or a sixth derivative, it gets kind of silly. So in that case, what you will see starting at the number 4 is just using the n itself, whatever number that is, up above the f. I don't want to make the mistake of calling that an exponent, although that's certainly what it looks like. We'll call it what it is, which is a superscript, something written above the basic line. So those would be derivatives in Isaac Newton's preferred notation. Gottfried Leibniz, who was German, in case you're wondering where that name came from right there, he preferred just to use y for the name of his function there. And there are benefits to both of these. One thing we've already talked about back in chapter 1, if you're going to use Newton's notation right over here, it is implied that that relation you're discussing is in fact a function, such that every x value gives you one and only one y value in that particular relation. Leibniz's preferred notation of y didn't really use the word function per se. This one could also be used to apply to any relation that's out there, including, and we certainly don't see many of these, you guys, but including relations that are not functions. Anyway, if you're going to use Leibniz's y, the first derivative is denoted as this kind of messy thing right here, which formally would be read as the derivative of y with respect to x. I'll say that again. It's the derivative of y with respect to x. But we all get a little lazy and we tend to just say that as dy dx. You don't really need to say dy over dx. That's kind of implied there. But these are the two ways, let me put a red box around them, these are the two ways most commonly that we are going to refer to our first derivatives, f prime of x or dy dx. If I were to ask you guys which one you like better, it's a little bit ironic because in Algebra 2, every one of you hated f of x and you wanted to just stick with y all the time. Somewhere over the last 2 years, I think many of you guys have learned that, oh yeah, there actually is a reason why why the f of x notation works well. And so most people at this level prefer the f prime of x of Newton over the dy dx of Leibniz here. But there's actually a good reason why that dy dx gets used. It's more useful to us with some of the more complicated problems that we're going to be doing throughout the year. But I digress. A second derivative in Leibniz's notation is very weird. There's a reason for this. It's a little odd, but we write it this way: d2y over dx2. Again, those are not exponents, so I didn't say squared, and there's a reason why we do the 2 on the d on top, but then on the bottom, it's really, don't write this down, that's really like this. It's really the whole dx that gets used twice. And I will explain why that is to you guys by the end of the chapter, but for today, nobody cares. And again, then, as you can see from there, for the nth derivative, this would just be dny up on the top over dxn there on the bottom. So those are the two primary ways we denote functions right here. I would say that these two methods are going to encompass 99% of all the functions and derivatives that we're going to see this year. There is, however, guys, kind of a sloppy way that a lot of the mathematical community has embraced, and I at least want you to see it. It starts off with Leibniz's notation of just using y for the function itself, but you will see occasionally this, y prime. And what y prime is, everybody, is kind of a combination of the two methods up above. We use y as the name of the original relation, and then we use the prime from Newton's method to talk about that. So it's weird. You will see this on occasion, and this is actually the way some of the older TI calculators used to work, something like y of 2. So let me just make something up. If y was equal to, 3x minus 5, well then y of 2 would be 3 times 2, which would be 6 minus 5. Y of 2 would equal 1. That's kind of a weird hybrid of those two methods. And likewise here, with that notation, you might see something like y prime of negative 5. Meaning whatever function ends up being your derivative, we evaluate that at negative 5. So you might see a y double prime, and then you might see a y with an n superscript as well. This method right here, you guys, really doesn't show up that much. As I said, the 2 on top probably make up 99% of our cases. Okay, so moving right along, everybody, let's see what we've got. And we're finally going to actually dive in now to our first problem. Now, we're going to start with the least complicated nonlinear function that we can come up with, and that would be f of x is equal to x squared. And I think I'm asking you guys 4 different questions here, if I'm not mistaken, all related to that same function, but we've got to pay attention to our directions here. Use the DOD, not Department of Defense, that means definition of the derivative in here, kids, to find f prime of x. And f prime of x is how we denote the derivative of the original function here, f of x. Now, what is very, very frustrating for you guys, and trust me, I know it and I felt the same way, you guys learned shortcuts for how to find derivatives last year in pre-calc. You guys are going to be very annoyed when I tell you that for certain problems, not all that many, but including all the ones that we're doing in 3.1, we are not using those shortcuts. The directions are going to tell us to use the definition of the derivative. And the reason why for that, everybody, is because if we really want to understand what's going on in calculus, we need to find methods that work for all functions. And those shortcuts that you guys learned, some of you know the answer already to this problem, most of you probably do, but those shortcuts that you guys learned last year in pre-calc only worked for certain types of functions, most notably polynomial functions. But they don't help you at all when you get to more complicated functions that might look like, wait a minute, I had one in here somewhere. Oh, later on in the chapter, we're going to do some trig stuff right there, and it's not going to help you out. So let's go ahead and cut our teeth here, everybody, on an easy one, learning how to use the definition of the derivative, and then it'll seem easier when we need it later on in the chapter. So again, we're trying to find f prime of x. So I'm going to start with the formula for f prime, which is the definition of the derivative. F prime of x is equal to the limit as h approaches 0 of, our numerator is f of x plus h, minus f of x, and our denominator is just plain old h. Now that's the generic version of the formula. Now we're going to go ahead and start making this more specific to this problem. So f prime of x will equal a limit as h approaches 0 of, and actually let me begin right here, guys. The f of x, which is the second term in the numerator, is the easiest thing in the world to fill in. Okay? We just need to put inside that red set of brackets what f of x is equal to. Well, it couldn't be put any more simply than this, guys. F of x is x squared. So x squared is what goes in that second set of brackets. What is harder, though, is figuring out what goes right here. F of x plus h. So we've got to figure this out, and that's maybe a little bit tougher. So it wouldn't be the worst idea in the world to go ahead and take a moment and say, okay, if that's f of x, then what is f of x plus h? Some of you guys are going to whip right through this and know the answer already, and some of us need a little bit of help at figuring this out. Everywhere there was an x, we're now going to replace it with the binomial quantity x plus h. Well, in this function, there was only one x, and the x gets squared. So here, something squared, and that something, the input value, is now x plus h. So that there in red, guys, that is what f of x plus h is. That's what we were looking for right here. So everywhere in the original function there was an x, we replaced that x with the quantity x plus h, and of course we still have to square it. And down in the denominator, it's just plain old h, and here we go. So that's the setup, everybody. Now this becomes a limit problem. And the first thing we should try when evaluating any limit problem is to simply do plug and chug. But I think you can see right away that if we do that, if the h's here both become 0, you end up on the top with x squared minus x squared. That's a 0. But more importantly, with a 0 on the bottom, and 0 over 0 is undefined, and so that's an inconclusive test. So now we need to pull out from our bag of tricks here in Chapter 2 some of the other methods that we've been talking about for how to evaluate a limit. And the number one way, especially when we're dealing with polynomials right here, is going to be through factoring and canceling. Now, we are not ready to do this just yet, everybody, in the entire numerator. We're going to go ahead and do a little bit of an expansion right over here of x plus h quantity squared. And I'm really hoping that everybody remembers that, I guess let's do it this way, that you learned it in Algebra 1 and again in Algebra 2. A binomial squared, everybody, is your first term squared plus, here's the fun part, the first term times the second term times 2. So that middle term here is a 2ab, and then it's the last term squared as well. And that, of course, is using the 1 and the 2 and the 1 from the third layer of Pascal's triangle, if you like to think about it that way. I really am not going to be happy this year, I'll tell you guys right now, if I have people tell me that a plus b quantity squared is equal to a squared plus b squared. That is the number one mistake, without question, that students make in Algebra 2. That was 2 years ago, everybody, and you need to know the difference between these things. A binomial squared always equals a trinomial. It does not ever equal a binomial. Unless you were dealing with imaginary numbers in there, but that's not happening here. So, back to this idea in mind here, everybody. Here we go. This first part of the numerator then is going to become an x squared plus a 2hx or xh, whatever you want to do, doesn't matter, and then a plus h squared. Okay, that's that. Then we've got a minus, and there's nothing to do with the x squared here, so that just tags along. And then down in the denominator, we have ourselves an h. And hey, guess what? Plug and chug still doesn't work. If you try to do plug and chug now, all your h terms would cancel. You'd still get x squared minus x squared on the top, which is 0 over 0, and we're no better off then. But we are making progress. The first thing I want you guys to notice is that your numerator now contains 4 terms. 2 of them don't contain the letter h. That would be the first term, x squared, and the last term, which is negative x squared. And when you go to combine those two, since they are opposites, they completely wipe each other out. And guys, that will happen every single time you use this formula on a polynomial function. Let me say that again. The non-h terms will cancel out every single time you do this on a polynomial function. Not with trigonometric functions, not always with rational functions, but with polynomials it will. So where are we now? We're at f prime of x is equal to a limit as h approaches 0 of, and rather than wasting my time writing 2xh plus h squared on the top, I'm wondering if you guys see what we can do right now to move us closer to a solution. Those two terms that are left in the numerator have a common factor of h. And I've said this to you guys before, I will say it many more times, factoring is almost always something that is worth your time and effort to do. Good things happen when you factor, everybody. So if we pull out an h in the top, that leaves us with a 2x plus an h all over the h that was down there on the bottom. And now what I'm hoping you guys see is that we have an identical factor of h on the top and the bottom, and they completely cancel each other out. So where are we now? That was ugly. F prime of x will equal the limit as h approaches 0 of 2x plus h. With the denominator gone, really the denominator is just 1, and that's perfectly fine, we now have a function, 2x plus h, that's continuous for all values of x or h or whatever. So we're going to go ahead now and let the h become 0. This becomes a 2x plus 0, which means that f prime of x, the derivative of f of x, is simply equal to 2x. So wow. That's the answer that I'll bet almost every one of you knew you were going to get 10 minutes ago when I first put this problem up here on the board. That the derivative of x squared is 2x, because those shortcuts you learned last year in pre-calc were really easy and really quick, and they stuck in your mind pretty well. But this is how we obtain that without taking any shortcuts, without making any assumptions, and this is how we kind of verify this result. And furthermore, this method here that we just used is universally applicable. This method that we just talked about would not work if f of x were a trigonometric function, or a rational function, or an exponential or logarithmic function. But the method that we just walked through will work in every single case. We're not going to get to verify all of those today, but we'll pick that up then pretty soon. Let me finish off the last three little questions here, and then I think we'll take a break and come back and finish it up in a second video here pretty soon. So this B, C, and D all are in reference to this problem that we set up right over here. So now that we've found our derivative, it says to find the instantaneous rate of change of this function at x is equal to 1.5. Okay. Well, one of the things we learned is that instantaneous rate of change is equal to the slope of your tangent, everybody. And the way we find the slope of a tangent is by evaluating our derivative, which was f prime of x, at this particular x value here of 1.5. And I should probably write down, just so we see it in front of ourselves here, that f prime of x was equal to 2x. That was the end result of that last long problem that we did. So if we want the instantaneous rate of change at x equals 1.5, we'll go ahead and simply evaluate our derivative, f prime of x, at 1.5, which is going to equal, let's take a look, 2 times our input value of 1.5, which is going to equal 3. And that, everybody, is our instantaneous rate of change of this function, f of x equals x squared, at the spot where x is equal to 1.5. We just found a rate of change using only one data point, not two like we had to do when we were finding an average rate of change. Let's go further. Part C, let's find the slope of the tangent to this curve at the spot now where x is equal to -1. So I'm looking at a different spot than I was in example B. Well, how do we find the slope of a tangent, everybody? We find that by taking our derivative, f prime of x, and evaluating it at whatever x value you need to, which for us here is -1. So again, the derivative was 2x. That's the expression. And we then use that expression and we evaluate it at -1. So it's 2 times -1, and we end up with -2 then for the slope of our tangent line. All right, that's where we're at. All right, and lastly, D, this is the question out of all of these that you're most likely to see. Find the equation of the tangent line, everybody. The equation of the tangent line, 2f of x, and now I just made up that x is equal to 1/2. So, this is a question we're going to see repeatedly throughout the course of the year. So I need you guys to ask yourselves this question. If I want to come up with the equation of any line, what do we need to know about it? And there's a couple of different ways of answering that question, but the most common answer, what do we need to come up with the equation of a line? The two things we normally need are a point and the slope. Those are the two things we need to figure out. So in order to figure out the point right here, let me go to green here, and I'm even going to label this out. The point of tangency is right here at x equals 1/2. So what we're going to do, guys, is figure out the point on the original curve by evaluating f of 1/2. Now the function f of x was just x squared, so 1/2 squared is going to get us 1/4. That means that our ordered pair, everybody, has an x value of 1/2 and a y value of 1/4. So that is your point of tangency. And that's one of the two things that we needed to figure out to come up with the equation of this tangent. The other thing we need, everybody, is the slope of your tangent. And that's similar to what we just did in example C. The slope comes from evaluating not the function itself, but its derivative, everybody, at the point of tangency. So the derivative was 2x. So this derivative is going to be 2 times our x value of 1/2, which equals 1. So now we know that the slope of our tangent is equal to 1. That's the second really important thing we needed to find. And take a look at where we are now, guys. We now know a point on this line, and we know the slope of this line. Where in the world should I go when I know a point and when I know the slope of my line? And the answer to that is something that some of you guys have been stubbornly avoiding for the last 2 or 3 or 4 years, but I'm going to do it every single time because it makes too much sense not to do, and that would be this, everybody, point-slope form of a linear equation. Now, we talked about this a little bit in chapter 1. Point-slope form is y minus y sub 1. It equals m times the binomial x minus x sub 1. It takes 3 values to be able to pull this off. You need to know the value of your slope, and then the x1, y1 is the ordered pair that you know your line passes through. So in this example, let's see what we've got. This is going to be y minus our y coordinate here, which is 1/4, equals our slope, which we found right here to be 1. I'll go ahead and put the 1 there just so we see it. And then x minus your x coordinate, which is going to be 1/2. Now, point-slope form, you guys, is really a means to an end. Although I need to be clear with you guys about something. If these were the directions that I typed on a quiz or a test, find the equation of the line tangent to f of x at x equals 1/2, then this answer that I have right here, if you boxed it up and submitted that, you would get full credit for that answer right there. Because you did what the directions said. You found the equation of the line. It's not the form that I'd intended it in, but if I'm going to want you guys to write it in slope-intercept form, I'm going to have to type that in the directions. Now that said, your book, 99% of the time, wants the answer in slope-intercept form, so I'm going to go ahead and do that real quick. So usually, as I said, point-slope form is the way we start the equation of our line, but then we simplify it to get it into slope-intercept form. So in most cases, we would distribute our slope, although that's meaningless here, and get an x minus 1/2, and then we would add this k value over here to the other side. And we'd get y is equal to, oh boy, a negative 1/2 plus 1/4 is going to get us a minus 1/4. And that, everybody, should be, if we've done this right, the equation of the tangent line to this curve at the spot where x is equal to 1/2. And what I'd love to do real quick, just before we wrap this one up right here, guys, is I'd love to talk for just a second about using the calculator to find out if our answer makes some sense. So let me shrink this over so you guys can actually see what's going on here. And I tell you what, I'm just going to start all fresh right here, and I'm going to open up a new document. And no, I don't need to save my changes. All right, and I'm going to put in a graph right here. Here was the original function we were dealing with, which is y equals x squared. I know, it blew your mind. Anyway, and what we think we've now come up with, everybody, is the equation of the tangent line at the spot where x was equal to 1/2. So I tell you what I'm going to do. I'm going to do menu, I'm going to do a trace, graph trace, and I'm going to put in 0.5 for my x coordinate and hit enter. Now I'm going to hit escape to get out of there. So that black dot, everybody, that's our point of tangency. And just to see things a little bit better, I'm going to go to number 4, Windows Zoom, and I'm just going to hit number 3, everybody, for zoom in, and I'm going to drag my cursor over to that point of tangency, and I'm going to tap the center of the D-pad, I don't know, 3 times maybe? Something like that, just so we can see a little bit better what's going on right here. So there's the point of tangency. And we think, we don't know yet, but we think we've come up with the equation of the line that is tangent to this curve at that point. And we think that equation here, everybody, is y is equal to x minus 1/4. So this isn't really going to prove anything, but it might satisfy your curiosity. I'm going to graph that line right there on the same graph. Y is equal to x minus 1/4. So I hit tab, all right, and here we go, x minus 1/4. And what I should see when I hit enter is the one and only line that passes through that point of tangency and is parallel to the curve itself at that particular point. Survey says, I don't know about you guys, I'm pretty impressed. I could probably get an even better sense of this right here if I did that zoom trick again. Menu, 4 and 3, zoom in, and if I continue to zoom in on the point of tangency, I think, and I hope, that's just going to reinforce our idea right here that we got this thing right. That the red line should be passing through the point of tangency, and that the red tangent line has the same slope as the curve itself at that point. In fact, the more I zoom in on this, boy, it's hard to tell the difference between the red line, which we know is a linear function, and the blue curve, which we know is not linear. The more we zoom in on that, guys, oh, that was bad. Let me do Control Z to undo that. The more we zoom in on that, the more it looks like that blue curve is actually like the tangent line itself. And that's a concept called local linearity that we're going to get to a little bit later. Okay, ladies and gentlemen, there are a few more slides to complete in section 3.1, but I'm out of time for right now. So I'm going to end this video and we'll pick that up on the next one here pretty darn soon.